Okay, I guess we can get started for this afternoon. Today's we're just have one class in the afternoon, right? It's on, I think. Yeah, we checked it. So I wanted, now the person that asked the question isn't here, but or is he? Maybe he's just sitting someplace else. But that issue about the external probability, I think it's right in the notes, okay, because what the calculation of that extrinsic probability that formed the message going from a check node back to the variable node was the extrinsic probability of that the variable node that you're passing the message to is a 1, given that the parity check is satisfied, okay? And if the parity check is satisfied, if you're computing the probability that that variable bit is a 1, that would mean that all the other messages at the parity check must have had odd parity. So when you add the 1 to odd parity, you get even parity, and the parity check is satisfied. And the expression there was for from that lemma that a set of variable nodes or a set of binary variables has odd parity. We use that odd parity expression. So that's the right expression. And then when we form the log likelihood ratio is always the log of the probability that a bit is 0 divided by the probability that it's 1. Okay, and we had computed the probability that it's 1. Okay, so the log likelihood ratio should be the probability of 1 minus p over p. And that is the way we had it written. So I think that's right. Anyway, I don't think there's a mistake there. Okay, today we're going to look, okay, introduce the notion of code ensembles. These are just sets of, large sets of codes that have similar properties. And you know, why do coding people deal with ensembles at all? Okay, well, basically the reason is because individual codes, particularly if they're big, they can be very hard to analyze their properties, like minimum distance or whatever. It's just difficult to compute these things. So what is often done is you consider a large set of codes that have certain properties in common. And then you can use an averaging technique. So you may not be able to compute the distance, say minimum distance of a particular code in that ensemble, but you can compute the average minimum distance over all the codes in the ensemble using statistical methods. And that allows you to say that maybe there'll be certain fraction of codes in this ensemble that'll have a given minimum distance. And so you know that if you select codes from this ensemble, you can find good codes. Okay, so oftentimes it's easier to use these large ensembles and use averaging techniques rather than it is to try to analyze specific codes. So Gallagher, and this is the way Gallagher approached his work. He constructed code ensembles rather than individual codes, and then he analyzed those code ensembles. So I think this is the guy that asked the question. So I think the expression is correct. Okay, it's P of, we're computing the probability that it's a 1, and the log likelihood ratio is the probability that it's 0 divided by the probability that it's 1, so it should be 1 minus P over P, which I think is the way we had it. Okay, so Gallagher constructed a JK regular LDPC code ensemble with block length n in the following way. The parity check matrix, he split it into J submatrices with this number of rows in each submatrix. M is the total number of rows in the H matrix. Again, we use M here rather than n minus k for the number of rows in the H matrix because when we do these random type constructions, we might get redundant rows. So it's not always, the number of rows could be a little bit more than n minus k. So the first submatrix contains subblocks of size m over j by k. Each subblock contains k1s in one of its rows. And then these subblocks are repeated diagonally until we have a set of k1s in each of the m over j rows. We'll see this, how this is done in a second. Then the other j minus 1 submatrices are obtained just by doing random column permutations of the first submatrix. So it is a random type construction. And so there's lots of codes. Any particular permutation gives you a code. And all possible permutations give you the ensemble. So you wind up with a code ensemble set of all possible parity check matrices which satisfy these rules. And this was Gallagher's original approach. So I guess I said this, what coding theorists like to do is analyze ensemble average performance. And again, why do they like to do that? Because it's just too hard to try to get the performance of individual codes. Okay? It's easier to do the averaging than to try to analyze a specific code when we're talking about large codes. So usually one tries to show that good codes, which would mean maybe codes with a certain guaranteed minimum distance, occur with high probability in the ensemble. Or oftentimes we say almost all codes in the ensemble are good, which means if you just picked one at random, you'd have a high probability that you have a good code or a code with a large minimum distance. So Gallagher's ensemble, if we illustrate it here for n equal 20, Gallagher's construction, j equal 3, that's the column weight, and k equal 4, the row weight. This is the regular code. So we have 20 columns. We divide it into, there's 15 rows divided by, oh yeah, I'm sorry. There's j, I was thinking there were m over j submatrices. There's not. There's j submatrices, m over j rows in each submatrix. So that's what we do here. We have j submatrices, 3 of them. Okay, the top one, the middle one, and the bottom one. And they should each have m, which is 15, the number of rows in this H matrix, divided by 3 or 5 rows, and they do. Each of these submatrices had 5 rows. And we can say in the first submatrix, he starts out with a 5 by 4 matrix which has 1s across the first row. And then he just repeats these with the 1s for each row. Second row, third row, fourth row, fifth row. That's the way he starts, okay, just to make sure that there's at least 1 1 in every column. And there's exactly 4 1s in every row. Okay, and then he gets the other 2, in this case, submatrices, are random column permutations of the first submatrix. So, for example, for these 4 columns here in the first submatrix, they could be randomly placed in these 4 positions in the second submatrix, and maybe in these 4 positions in the third submatrix. That would be one way of doing it, okay? And then you do this for every set of columns. So you take these 4 and permute them again here somewhere and here somewhere, always using up columns that haven't been used yet. And you do this for all of the columns in the first submatrix. So all ways of doing this, and you can count. You could count for a given n and k and j, you could count how many possibilities there are for rearranging these columns in the second and third submatrix. So the first submatrix is fixed, but there's many different combinations for the second and third submatrix. That defines, all those possibilities define the ensemble of codes. So here's some other ways of arranging the columns here. And again, just illustrating it here for the first subblock, rearranging the columns of the first subblock, but we'd be doing it for all the subblocks. Okay. But it's done separately for, I mean, you could think of different ways of doing this. You could, and the way he decided to do it gave him the easiest way of calculating the average properties, or at least it gave him a way of calculating the average properties which gave him the best results in terms of minimum distance. But you could just permute the columns for both of these together. Otherwise, if this column went here, it would also have to be repeated down here. Okay, but it turns out to be a better ensemble with better properties if you don't do that, if you do these permutations separately. Okay, so what he was able to show with this construction of an ensemble is that for if as long as j is greater than 2, so the column weight it has to be 3 or more, and as the block length n gets large, the minimum distance that's typical, so most of the codes would have this, is lower bounded by this expression. N is the block length, and delta min is a number bigger than 0. It's a fraction, but larger than 0. And it's a constant that it depends on j and k, how you pick these parameters, but not on n. So what you find is that most members of this ensemble constructed this way will have a minimum distance which is least equal to n times this number, whatever it is, whatever it turns out to be. And this number is called the minimum distance growth rate. And again, you can calculate this number for...
Last slide.
Yeah.
Every time m, the number of rows, is divisible by g?
Well, it would you'd construct the thing that way. Otherwise, you would consider a parity check matrix where m was a multiple, the number of rows was a multiple of j. So if j is equal to 3, the number of rows has got to be a multiple of 3. Yeah. So there are some restrictions. I mean, if you took m equal 3, you couldn't start with a matrix with 11 rows, for example. So this is called the minimum distance growth rate of the code. And now there are lots of different ensembles of LDPC codes, not just JK regular codes, have minimum distance growth rates associated with them. And this is kind of a general parameter that we use for those growth rates that have properties, or for those ensembles that have properties like this. But if we're talking about a JK regular ensemble, we sometimes use this notation to indicate this growth rate. So why do we call it a growth rate? Well, it's just the rate at which the minimum distance is guaranteed to grow as you increase the block length of the code. And that's a good parameter. It's something important, because as you consider a certain type of code design and you make the code longer and longer, you want the minimum distance to get larger and larger. Okay? You don't want to make a bigger code which is going to be more complex and not get any larger minimum distance. And that does happen sometimes with some constructions. If they have too much structure to them, the minimum distance is bounded above by some number, and no matter how large you make the block length, you're never going to get more than that minimum distance. So that oftentimes is a problem with codes which have a lot of structure. Again, the idea of putting structure in is going to make it easier to implement the encoder and the decoder. But the downside is sometimes you don't get the best minimum distance when you do this. So this kind of random type construction does guarantee that we can get as large a distance as we want if we make the block length big enough, assuming that the ensemble has a delta min greater than 0. So for 3/6 regular codes, which is a very common, remember j has to be at least 3. And the 3/6 regular would be the ones whose nominal rate is a half. the delta min is 0.023, which means if you had a rate of a length 1,000 code, if you chose a rate 1,000 code from this ensemble, you would have a high probability that your code would have a minimum distance at least 23. If you chose a code of length 10,000, you'd have a high probability that your code would have a minimum distance of at least 230. So this is the nice thing about these types of ensembles that have the so-called linear growth property. They're called asymptotically good for this reason. Yeah, we'll get to that in a second. Yeah, yeah. So with maximum likelihood decoding, then we're going to get good performance. Minimum distance doesn't really guarantee anything with suboptimum decoding, like message passing, but we would at least know that with maximum likelihood decoding, we'd have a certain guaranteed performance. We could correct so many errors if we're talking about a binary symmetric channel. And if we have a good suboptimum decoder, then that would also be expected to perform well. So again, after having said in the beginning of these lectures that minimum distance isn't the total answer, and that's part of the reason why these LDPC codes are of interest. They have this sparse property, and similar with turbo codes, gives you very good performance at moderate error rates, close to capacity. What the minimum distance does is it guarantees you good performance at much lower error rates, okay? But that's important too, okay? And so the regular codes all have good minimum distances. Now when we talk about the irregular codes, we'll find out that they don't have, in general, they don't have this property of linear distance growth. They're not asymptotically good. So their performance at higher signal-to-noise ratios is generally not very good. Okay, so if you want to achieve very low error probabilities, 10 to the minus 10, say, it sometimes is difficult to do that efficiently with irregular codes. We'll talk more about this trade-off in these different kinds of properties. In terms of the writing, let me just make sure again. It just says minimum distance growth rate, and yeah, I guess these are readable here. This is minimum distance. This just says, with ML decoding, we'll achieve excellent performance because you have a large minimum distance. And this is asymptotically good. Okay, it just means as you make the codes large, you're guaranteed to have good codes because you're going to have good minimum distance. And again, as I said, finding the minimum distance of a particular code with large block length is impractical. I mean, there's not much structure to these codes. So how would you do it? Well, you'd have to kind of list them all and count their weights. And if we're talking about this one here, 10,000, there'd be 5,000 information bits. You'd be talking about 2 to the 5,000 code words that you'd have to write out and see what their weights are. Okay, and but the ensemble average technique tells you that you're going to get, with high probability, right about this minimum distance if you choose a code randomly from this ensemble. So the way Gallagher did that, and we're not going to go into the details. Again, because its model is the minimum distance of an ensemble member. He modeled as a random variable, and then he was able to bound the distribution function of the random variable, and he got a function which looks like this. It kind of starts low, and then at a certain point it peaks up to get close to 1, and then it levels off. Okay, and as the block length n goes to infinity, for large block length, it actually approaches a unit step function, which means this probability, this is the probability that the minimum distance is at least a certain amount. And the probability that the minimum distance is, no, let's see, I'm not saying this right. Otherwise, the probability that we select a code, when this gets to be a unit step function for large n, the probability that we choose a code, if we chose one randomly, that had minimum distance at least this amount, okay, would be essentially 1. Okay. And so that you can guarantee then, well, with high probability, well, you can guarantee it if you let n go to infinity. But for large n, with high probability, you're going to get a code with at least this minimum distance. Okay. So this is the number of codes with minimum distance smaller than that. And that goes to 0, okay, as n goes to infinity. The probability that finding a code with minimum distance smaller than this goes to 0. So again, this is just n times that growth rate, delta jk. So this is, again, says that almost all codes in the ensemble have a minimum distance at least equal to this number. Now, what are some of the numbers? Okay, we said 1, and what do they mean? Okay, so this is for, these are growth rates that are calculated using this averaging technique for all, or for a bunch of different JK regular codes. And here's rate, and here's the growth rate, the minimum distance divided by n, this delta JK. The guaranteed growth rate for codes in this ensemble. Here's the one we looked at earlier, the 3-6 regular codes. They have a growth rate of 0.023. Now, if you do the construction to be denser, still rate a half, say 4.8, you get a higher growth rate up to about 0.06. Okay, and if you make it denser yet, say to 5.10, you get even a higher growth rate, which is about 0.08. So you get, I think this is the question you were asking, you get larger guaranteed minimum distance growth rates with JK ensembles if you make J and K bigger. Okay, so that's good. The downside is the larger J and K is, the more the complexity is. So the complexity depends on J and K. There's more ones in each row and more ones in each column. That means there's more operations. Remember, as we're doing these updates, these node updates, the number of messages that we have to pass from one node to another is either J or K. If it gets larger, we get more complexity. So, but it does make sense that as we add complexity to the code design, we should be able to get better properties, distance properties, and we do. And you can, these are growth rates for all different kind of, here is, this is like rate 2/3, and if we have a J equal 3 with a 3.9 code, we get a pretty small growth rate, but if we go to a 4.12, we get a larger growth rate. So these are all asymptotically good ensembles. All JK regular designs based on Gallagher's construction are asymptotically good ensembles. And as the density J and K gets larger, the growth rates approach this blue line, which is the Gilbert-Varshimov bound. Now this is what you're guaranteed to be able to achieve with the entire class of block codes, NK block codes. No restrictions at all. Okay. So otherwise, saying if you consider the entire ensemble of block codes and you choose a code randomly out of that ensemble, you have a high probability of finding a code with this minimum distance. Okay. This minimum distance growth rate, depending on the code rate, using the word rate in two different ways here. This is the code rate, and this is the growth rate, that delta min of the ensemble. So like with the Gilbert-Varshamov, for the general ensemble at rate of half, you should be, if you pick a code at random out of the general ensemble, you should be able to get a growth rate of 11%. Okay, so again, why would we want to fiddle with these low density codes which have something less than 11%? Well, they're much easier to decode. In general, if you just pick a code randomly out of the ensemble and you try to do maximum likelihood decoding with it, you're going to have decoding complexity that grows exponentially with the block length. Okay, with low density parity check codes, we know we have a decoding method. It's not maximum likelihood, but it's a very good decoding method. Belief propagation, which has only linear complexity and block length. So it's a huge difference in complexity. So you pay a little penalty in distance, okay, but you get a big gain savings in terms of complexity of decoding. So that's kind of the idea, was Gallagher's original idea with regard to invention of low density parity check codes. Of the block length? Yeah. I mean, these numbers assume infinite block length. Okay, so this is the growth rate, the delta. So it would say that if, and it's the same for the Gilbert-Varshamov bound, if you're if you have very large block lengths, the distances predicted by this are going to be very accurate. You have a high probability of getting that distance or better if you have a large block length. If you're using ensembles with shorter block lengths and you pick one at random, you may get one that does not have quite as good a distance as what's promised here. But it's the typical type of asymptotic result that information theory people love to try to use, because it's just too hard to try to compute these things for individual codes. Again, as I said, that example, we'd have to do 2 to the 5,000th.
Asymptotically good.
Pardon?
Asymptotically good. Asymptotically good.
The asymptotic, you said the...
He's asking what is meant by asymptotically good.
Oh, that's what I just that you have this property that the minimum distance grows linearly with n. Not every code, all the JK code ensembles have that. That's kind of built in, that's assumed when we draw a graph like this. But some of the irregular low density parity check code ensembles, most of them as a matter of fact, do not have minimum distance growing linearly with n. And turbo codes don't either. Okay, so they may grow as the square root of n or something like that. Or with some logarithmic function of n. But not linearly with n. So linearly with n is a really desirable property in terms of distance growth. And these kinds of low density codes have that property. Now, okay, so that's distance. Now the other side of the, and like I said, that primarily relates to the performance you can expect to get out of these codes at high signal to noise ratios, which would be when you were trying to achieve very low decoded bit error rates, maybe 10 to the minus 10. Of course, it's also important for a lot of applications how well you do at lower signal to noise ratios when you have more noise. And as I've been saying, minimum distance isn't the only story then. When there's a lot of noise, if any code word close to the transmitted code word, not just the minimum distance one, may cause an error if you've got a lot of noise on the channel. So it's more the weight distribution rather than the minimum weight that affects the performance at lower SNRs. Now, one way to get a handle on how the performance of a iterative decoding algorithm works in decoding one of these low density codes is to use something called density evolution. It basically tracks probabilities, probability density functions as you go through the iterations of an iterative decoding algorithm. So this is a technique for analyzing iterative decoding algorithms, and that's the way we're decoding these codes. We'd like to decode them using maximum likelihood decoding, but it's too hard to do. It's impractical. So there's a technique been developed that allows us to analyze how well this belief propagation iterative algorithm will do with these low density type codes. And the result again is asymptotic, like this distance result. Otherwise it's accurate if we're using very large block lengths, but if we use shorter block lengths it may not be as accurate. So we're going to assume an ensemble of Tanner graphs, which is just an LDPC code ensemble. We'll think of it from the graph point of view. Memoryless channel, and we assume the graphs are cycle-free, so we're assuming large block length. So the technique here does not take into account the correlations, and that's why it doesn't hold up as well for practical codes of finite length, which we know have cycles. However, it does give us a benchmark as to how well we could, in principle, perform if we didn't have cycles. And if we can show performance which is pretty close to that, we know we're doing almost as well as we could do without any cycles at all. So what we want, for a code ensemble, we want to determine a threshold, an iterative decoding threshold, which we could think of in several ways. The maximum noise level for which we can possibly correct errors in this code ensemble. Okay, we could think of it as the minimum signal power needed to correct errors also. Minimum signal to noise ratio. So we're going to look at it, of course, on the erasure channel because it's much more complicated mathematically. The procedure's the same. It's just that the math gets more complicated, even for the binary symmetric channel and certainly for the Gaussian channel. So in the erasure channel, we know there are only 3 messages that we pass. We're going to let Q sub L be the probability that a check to a bit message is an E at iteration L. So we're tracking things here iteration by iteration. P sub L will be the probability that a bit to check message is an E at iteration L. So at iteration L, a message from check to bit, well, this is just recalling what we had from this morning. In erasure channel, the message that goes from the check node to the variable node is going to be an erasure, remember, if any of the other k-1 incoming messages are an E. So that means from the k-1 variable nodes that we're not sending so our check node is trying to send a message to a particular variable node. The previous messages that we got from all the other variable nodes connected to this check node, if any one of them was an E, okay, then the message that an erasure, the message that we would transmit would be an erasure. That's the rule we used this morning. So now, assuming that incoming messages are independent, and this is why we have to assume that there aren't any cycles in the code, because for the first iteration, we could make this assumption. It's a memoryless channel, and these things are all independent. But once we get go around a cycle, then we no longer can guarantee independence. Okay, but we make that assumption. Okay, the probability that no incoming message is an E. Okay, P sub L would be the probability that an incoming message is an E. By the way, okay, these L's aren't very visible, I know, in the notes. So these superscripts are L's. And this is, of course, k-1. This is the probability that an incoming message is an E. 1 minus that is the probability that's not an E. And if we, assuming independence, if we raise that to the k minus 1 power for these k minus 1 messages that are sent from variable nodes to this check node, we get the probability that no incoming message is an E. Okay. Now this says that the probability that at least one of the incoming messages is an E is 1 minus this. This is the probability that no incoming message from the other k minus 1 variable nodes is an erasure. 1 minus that is the probability that at least one is an erasure. So this, therefore, is the probability that our check node is going to pass an erasure message back to the variable node. So we can calculate this exactly with these probabilities for the erasure channel. So now if we talk about messages from bits to checks, I guess we just did. This was from checks to bits. Now the other messages are the P's, the bits to checks. We want to find the probability that that's an E. Well, the original message, we pass an erasure from a bit node to a check node. Remember, if we got an erasure on the channel, and if all the incoming messages from the check nodes at the previous iteration were also erasures. Remember, if anything wasn't an erasure, then we knew its value. If it was a 1 or a 0, we'd pass that as the message. So we pass an erasure only when we have an erasure on the channel, then that stays with the variable node throughout decoding, and that probability is just epsilon, our channel erasure probability. And all the messages that we get from the previous iteration from the check nodes connected here are an E. Okay. Now again, assuming independence, this is the probability of erasure from the channel. Okay. And this is the probability that we get an erasure from a connected check node on the previous iteration. So this is iteration L, this is L minus 1. This is the Q from the previous iteration. We just gave the expression for the Q. Okay. And again, assuming independence, we take this probability, raise it to the j minus 1 power. Again, we're not using one of these messages from the check node that we're passing our message to. We're not using that one. We're just using, again, this is the extrinsic information idea. We're just using the other j minus 1. So this is the probability that all the incoming messages from the check nodes, other than the one we're sending the message to now, were erasures. And this is the probability that the channel has an erasure. So the product of these is going to be the probability that we're going to send an erasure at iteration L. Now this, in turn, from the previous expression was given by this, so we can plug that in. So this is 1 minus this. And again, this is an L here. I can't even read it on the slide. This is L minus 1 for iteration L minus 1. This is K minus 1, because that's what we had here as the exponent, where K is the check node degree. And this whole thing gets raised to the j minus 1 power. So we now have expressions for the messages that, probabilities that we send from variables to checks and the probabilities that we send back from checks to variables. And so what this, in general, now we start out with the very first iteration. This is, I mentioned to David that to me this doesn't look like an L, but it's an L, okay? Iteration 0, otherwise in the beginning our message is just epsilon, okay? And then at later iterations, because that's what we got off the channel, at later iterations, when we have messages from previous iterations from check nodes, we have this expression, which is just this thing. Now we can use this method of tracking the probabilities of messages passed in the belief propagation decoding algorithm to determine, I mean, these things are functions of epsilon, which is the channel parameter. Think of it if we were doing a Gaussian noise, additive white Gaussian noise, we'd have a signal to noise ratio parameter here. Or we'd have noise variance sigma or something like this. It allows us to determine the values of epsilon for which the message passing decoder is likely to correct errors and how many iterations are necessary. What do I mean by likely to correct errors? Well, we'll see that if the probability of passing erasures goes to 0, that means that we're correcting them. Okay. And we'll be able to track how fast this happens in terms of iterations. Somebody was asking about this earlier, I think. So let's do an example. Let's suppose we've got a 3/6 regular code ensemble. I mean, again, this is all done assuming we're operating with some code within a particular, an ensemble with some particular properties. Well, this whole development assumed a JK regular ensemble because we've got the parameters J and K here. It's different. It's a different method if we have irregular ensembles. It's essentially the same method, but the parameters are different. And let's say that the erasure probability is 0.3. Now, on an erasure channel, the capacity of an erasure channel is 1 minus epsilon. So if you'd have 30% erasures on a channel, you should be able to transmit at a rate of 0.7, or anything up to rate 0.7. If you code properly, you should be able to communicate reliably. So this is a rate 1/2 ensemble. The erasure probability is 0.3, which means the capacity would be 0.7. So we're quite a bit below capacity. So we can think that, yeah, we're probably going to do pretty well here. Well, let's see what happens. The probability the code word will stay erased after L iterations is given by this expression. This is the erasure probability for a code bit. These are the P's. In the beginning, 0.3. This is the probability off the channel. And then in general, it's given by this expression, which is exactly that expression on the previous page, except now we have, for k minus 1, we have 5, because k is 6. And for j minus 1, we have 2, because j is equal to 3. And again, this is L minus 1 in here. So we just compute them iteratively. We start out with P0 and recursively go through this equation, and these are the numbers we get. And we can see that after 7 iterations, at least to 4 significant figures, that's never going to be truly 0. So it depends how reliable you want to be. And you can, this is a parameter you can set when you do density evolution. You can set a desired error probability that you're shooting for. For example, you may say, well, what's important to me is 10 to the minus 8 error probability. So you could keep doing this until you get to 10 to the minus 8. Okay, and if you get that low, that tells you that you should be able to get that error probability for that epsilon, for that channel. Okay. So after 7 iterations, the erasure probability goes to 0. Now this assumes that we've got a code with no 14 cycles or less, because we're assuming independence here, which is most codes will not have girth 14. So that, again, for finite length codes, you can't guarantee this. Okay, but it gives you an idea, particularly if you have large, randomly chosen codes, what you can expect to do. Now, we can plot this as, so we say, all right, well, 0.3 is pretty easy. How high can we go? And we know if we had a maximum likelihood decoder with a rate 1/2 code, we should be able to go, because the capacity would be a half, or we should be able to go as high as epsilon 0.5, because that would give a capacity a half. So as long as we're operating at rate a half or below, we should be able to get up to epsilon 0.5 if we had maximum likelihood decoder. Okay, but this is iterative decoding, so let's see. This is the erasure probability, and this is iterations. And these are the numbers we just calculated. We started out at 0.3, and we went down here, and after 7 iterations, we were essentially at 0. Okay. Now, if we raise it to 0.42, we get these numbers. Okay, and we get down here, and it takes now more iterations, about 30, but we still get to 0. At 0.43, we don't. Now, you could say, you could keep going, okay, but it doesn't appear like you're going to ever get there with this, certainly not with a reasonable number of iterations. So again, it depends how you actually apply this method. You have to decide kind of what error probability you're willing to stop at, willing to consider reliable. Is it 10 to the minus, in this example, once we got to 10 to the minus 4, essentially, we stopped. But you may want to say, I'd rather have 10 to the minus 10 or something. You'd have to do more iterations. And you want to say how many iterations are you going to do before you give up, in a sense, and you see that the rate of decay is too small to ever get you to 0 in any reasonable number of iterations. It looks like then that for large enough epsilon, the erasure probability doesn't go to 0, for example, 0.43. And it turns out if you do this, if you really fine-tune it, you can calculate the threshold as 0.429. Otherwise, up to an erasure probability of 0.429, you'll get the erasure probabilities going to 0, which is short of capacity. Capacity, we could have, with maximum likelihood decoding, we could have got there even with epsilon close to 0.5. So that's the penalty we're paying for having a suboptimum decoding algorithm.
But is it mandatory that we should have cycles of length that is coming from the structure? For a 7th iteration, that probability has to become the same. If it is
Yeah.
mandatory that cycles of length 14 shouldn't be there.
Right. Otherwise, yeah, right. So the analysis assumed that you had no cycles.
Yeah, but the structure for the design
So in a particular code, you would have cycles. So if you're operating a code on the erasure channel whose length is 1,000 or something like that, you're not going to be able to get a low error probability all the way up to 0.429. It'll be somewhat less than that. And this brings up the whole issue of finite length analysis. I mean, the asymptotic analysis tells you basically what you can expect if you use large codes. But if you're constrained to shorter code, shorter block lengths for reasons having to do with a particular application, short latencies, whatever, then this doesn't give you the whole picture. It gives you some guidance. I mean, codes that are good asymptotically, the same structure is probably going to be good in a finite length regime too. But there's that's a very active research area right now in coding and information theory is, can we say more about what makes performance good in a finite length regime? But it's true here that, so this analysis would primarily be accurate for large code lengths. It's always that way, though. I mean, you can't get close to capacity with short codes. I mean, you have to use long codes and powerful codes to get close to capacity. So these are just some numbers, again, for different ensembles. These are BEC thresholds. The Shannon capacity is always 1 minus R. These are some kind of common JK regular ensembles with the corresponding rates and their iterative decoding thresholds. And we see that there's a fairly large gap to capacity. We don't get that close, okay, with JK regular codes. And also, if you fix the rate and go to higher density codes, like we did with when we were looking at the minimum distance, and we saw that, oh, we were able to improve the minimum distance going to higher density. Here we lose. We get worse thresholds as we go to higher density. So we get a trade-off between the iterative decoding threshold, is kind of how well we can expect to do at moderate error rates, and the minimum distance properties of the code, how well we can expect to do if we want to operate at high signal-to-noise ratio. So we'll talk more about this when we look at different examples. So here's just some simulation results, and to try to put it in perspective. This is channel erasure rate. This is the iterative decoding threshold for 3/6 regular codes that we just calculated, 0.429. So we should be able to, with a large code, we should be able to get a low bit error probability, or I mean, there's no errors in an erasure channel. You just have bits that are still erased after you finish decoding. We should be able to get low bit erasure rates pretty close to this channel error rate with a long 3/6 regular code. And here's a simulation which shows 36,000 bit code. Okay, these are rate of half, so there'd be like 18,000 information bits. And we get, at that length, we get pretty close. I mean, we get 10 to the minus 3 erasure rate within almost 0.01 difference. You know, this is 0.429. This is about 0.41, maybe 0.415 or something like that. So we can get it. We get a 10 to the minus 3 erasure rate pretty close to the iterative decoding threshold. So that's, with 36,000 bits, we do about as, you know, we could get even a little better if we make this 360,000, and if we make it 3.6 million, we get even a little closer. But we're not going to go beyond this with iterative decoding. Now, you can also calculate these thresholds for map decoding. It's a different type of analysis because it's not an iterative decoder at all. But you can calculate thresholds of map decoding. Now, if you use the ensemble of all, if the ensemble you were considering is the ensemble of all possible block codes of a given length, your map threshold would be capacity. That's what the capacity theorem says. But suboptimum ensembles, like 3/6 regular LDPC codes, they are not capable of getting to capacity even with map decoding, because they pay a penalty. We saw the penalty they pay in terms of minimum distance, say, for the nice structure that they have to make it easy to decode. But their map decoding threshold is pretty close to capacity. Okay, it's almost 0.49. So if we could map decode these codes, we'd be happy. Okay. Pardon? Yeah, almost at full capacity. And what we'll see on Tuesday is that we can get to this with 3/6 regular codes. We have to do it using a technique called spatial coupling. Okay. And that's, we'll have a lot more to say about that when we come to that point. Now, the next example here, remember we said with 510 we make the code more powerful. We're going to get, but the threshold is worse. And this is a simulation for 510 codes. Now, you may say, well, wait a minute here. You said that these have more distance than these. And you're showing that the performance, and that should be good at some level, but the performance is much worse. This is operating, it gets 10 to the minus 3 at about 0.33, and here you're 0.415 or something like that. So what's the story? Well, the story is that if you extended these curves down, this is the only down to 10 to the minus 3. If you extended this down to 10 to the minus 20, say, this guy is going to become essentially vertical. This guy will have a slope, a small slope. They will eventually cross. So this will eventually be better. I don't know where it would be. 10 to the minus 10, 10 to the minus 20, 10 to the minus 30. Okay? But even though there's this quite a gap here in performance at moderate erasure rates, if you really pushed it down, and otherwise what's going to happen is this one's going to move way over, it's going to eventually come, it'll have a slope that'll eventually put it to the left of this curve. But if we were able to do map decoding of these things, the map threshold is actually better. So this is, again, another nice thing in the spatially coupled thing. If we can do spatially coupled with this, we can have a better threshold than the 3.6, and we get better distance. So we don't have this trade-off. And that's the last slide for today. Are there any questions?
Are these map thresholds calculated using some union plotting technique, or how do they calculate?
I think so, yeah. I haven't really read the papers. It's, Igal Sasson. Yeah, I mean, he written a number of papers on these, and yet using some kind of union bound or Chernoff bounding technique, similar, I think, to the error exponent type of analysis. And he is able to compute those thresholds.
That's why probably, because the stronger code, you see a better.
Yeah, I mean, it makes sense that the map threshold of the 510 would be better than the 3.6 because it's a stronger code.
Is there any technique by which we can know what length of my code is going to ensure certain user probability given certain number of iterations?
Well, there has been finite length analysis done on low density parity check codes. Papers by Olmos, O-L-M-O-S, and Urbanki. They've had papers come out in the last 5 years or so that analyzes the finite length performance of these codes and how they scale with block length, how the error probability scales with block length. So those are very nice papers. And so instead of having to do a simulation for every different block length, now they're bounds, they're not exact, but, and they're primarily for the erasure channel, but you can get an idea of how much improvement you get in performance as you increase your block length. So that's some of the finite length analysis that I was referring to that people have been concentrating on in recent times. Well, we wouldn't have an error floor because it's a regular code and it's asymptotically good, but it'll have a slope. It doesn't show up so much here. I think, it depends how you draw these things, how you scale the x and y axis. If I drew it differently, you'd see more of a slope. But it does have a slope to it, and it's not the slope of the 510 is steeper. So it's not so evident looking at this picture. But I think if you studied it carefully,
This probably will have an error flow, like after some time it will.
well, it won't because it's regular though. Yeah, I mean if it was irregular, it would have an error floor and it would just cross. But it shouldn't have a dramatic error floor anyway. But it will cross eventually. Yeah. I think so. Anyway, I don't know. I don't know how you analyze it. What's going to happen at 10 to the minus 20 or 10 to the minus 30? It should. Any other question? Yeah.
Does this directly translate to the binary code LDPC and
Does it translate to what?
binary input LDPC
Yeah. It's the same. I mean, just the numbers are different. And we'll give some. I think I've got more on AWGN channels in the last day on Tuesday. More simulations for AWGN channels on the spatially coupled code part of the lectures. Here, focusing more on the erasure channel, but it's basically the same. Anything else?